Hello and welcome to the Drone Builders Collective. Whether you are tightening your very first bolt or fine-tuning a custom carbon fiber frame, you have found your crew. Before we dive into the hangar today, make sure to hit that like and subscribe button on whatever platform you are listening on. That way, you never miss a lesson in building the ultimate flight machine. This is the podcast where we break down the high-flying world of aerospace engineering into pieces you can actually use on your workbench. Every single week, we dive deep into the art and science of making things fly. We will explore aerodynamic principles, aircraft design, and robotic functions. You don't need a fancy degree to build something incredible. You just need the drive to learn, create, and launch.
Welcome to Aerodynamics and Flight Lesson 5, Wing and Aircraft Geometry. A wing is not just a flat surface attached to an aircraft. Its size, shape, angle, placement, and structural layout influence nearly everything the aircraft can do. A wing can be long and narrow, short and broad, straight, swept, tapered, twisted, angled upward, angled downward, mounted high on the fuselage, or mounted low. Those choices affect drag, stall behavior, structural weight, high-speed performance, roll stability, passenger comfort, landing gear arrangement, engine placement, and even what kind of airports the aircraft can use. There is no universally perfect wing. A glider's wing looks different from an airliner's because their missions differ. A fighter's wing looks different from both because it must support high-speed flight and aggressive maneuvering. A crop-spraying airplane, a military transport, a sailplane, a drone, and a supersonic aircraft all reflect different compromises. This lesson explains the major parts of wing geometry and how designers use them to shape aircraft behavior. Wing geometry is a set of choices. When engineers describe a wing, they use several measurements and angles. The terminology can seem technical at first, but each term describes something you can see. The major geometric features include wing area, wingspan, chord, aspect ratio, planform, taper ratio, sweep, dihedral or anhedral, incidence, twist, wing placement relative to the fuselage. The details matter because the wing is a force-producing structure. It must create lift efficiently, resist bending and twisting, remain controllable near stall, avoid problematic behavior at high speed, and fit into a complete vehicle. NASA describes wing geometry as one of the chief factors affecting lift and drag. The standard definition of aspect ratio is wingspan squared divided by wing area. Dihedral and anhedral describe whether wing tips angle above or below the wing root. 1. The wing's geometric design is therefore not a cosmetic decision. It is one of the highest level design decisions in an aircraft program. Wing area. How much surface carries the aircraft? Wing area is the total planform area of the wing when viewed from above. In other words, if you look down on the aircraft and trace the wing outline, the enclosed area would be its wing area. Wing area has a direct connection to lift. A larger wing has more surface over which it can create pressure differences and turn air downward. All else equal, a larger wing can produce a given amount of lift at a lower airspeed or lower angle of attack. That is why slow-flying aircraft often have relatively large wings. A bush plane that must take off from short, rough strips needs low stall speed and strong low-speed lift. A glider needs enough wing area to fly slowly and efficiently in rising air. A surveillance drone may use a large wing so it can remain airborne for long periods with modest propulsion power. But more wing area creates costs, more structural weight, more skin friction drag, more material and manufacturing cost, more potential for aeroelastic flexibility, more space required for storage and parking, more loads at the wing root. A smaller wing can reduce some of those costs and may be useful for high-speed flight, but it must carry more weight per unit area. That generally raises stall speed and increases takeoff and landing demands. The relationship between aircraft weight and wing area is called wing loading. A high wing loading means a relatively heavy aircraft supported by a relatively small wing. A low wing loading means the aircraft has more wing area relative to its weight. High wing loading tends to mean higher takeoff and landing speeds, higher stall speed, better penetration through turbulence in some conditions, more compact wings, potentially better high-speed efficiency, depending on the design, greater demands on runways and high-lift devices. Low wing loading tends to mean lower stall speed, better low speed and short field performance, lower sink rate for gliders, more sensitivity to gusts and turbulence, larger wings for a given aircraft weight, potentially more structural and storage challenges. A large transport aircraft can have high wing loading yet still land safely because it uses sophisticated flaps and slats to make the wing produce very high lift during approach. A small trainer can have low wing loading and simple flaps because it is meant to be forgiving at low speed. Span and chord. The wing's major dimensions. The wingspan is the distance from one wingtip to the other. It is the full left to right width of the wing. The chord is the front to back distance from the leading edge to the trailing edge. Because many wings change shape from root to tip, they may have several chord values. Root chord is the chord near the fuselage. Tip chord is the chord near the wingtip. Mean aerodynamic chord is a calculated representative chord that helps engineers describe the wing's overall aerodynamic behavior. For a simple rectangular wing, chord is the same everywhere. A rectangular wing is easy to manufacture and easy to understand, which is why it is common on simple training aircraft and some utility aircraft. But rectangular wings are not always ideal. They can be structurally heavier than a tapered alternative, and their lift distribution may not be as efficient. They can also create strong lift near the tips, which can contribute to undesirable tip stall behavior unless designers use twist, airfoil changes, or other stall control measures. Span and chord work together to determine the overall proportion of the wing. A wing with large span and short chord is long and slender. A wing with short span and long chord is compact and broad. That leads to one of the most important wing parameters, aspect ratio. Aspect ratio. Long and slender versus short and broad. Aspect ratio is a measure of wing slenderness. It is usually expressed as, for a simple rectangular wing, it can also be thought of as wingspan divided by chord. A higher aspect ratio means the wing is longer and narrower. A lower aspect ratio means it is shorter and broader. Aspect ratio strongly affects induced drag. Long, slender wings produce less induced drag for a given amount of lift than short, broad wings. That is because the wingtip vortices and downwash have less influence on the wing as a whole when the lifting force is spread across a greater span. High aspect ratio wings are common on sailplanes and gliders, long-endurance surveillance aircraft, many airliners, high-altitude research aircraft, some electric aircraft designed for range and efficiency. Low aspect ratio wings are common on fighter aircraft, high-speed aircraft, many aerobatic aircraft, carrier aircraft with space constraints, delta-wing aircraft, vehicles where structural compactness matters. NASA notes that higher aspect ratio generally produces lower drag, higher lift-to-drag ratio, and better glide performance. Gliders are the classic high aspect ratio example. 1. The difference is easy to see in silhouette. A sailplane has wings that look almost impossibly long relative to its small fuselage. A fighter may have wings that are much shorter and broader, sometimes blending into the fuselage. But aspect ratio is a trade-off, not a scorecard. A long wing reduces induced drag, but it also bends more. That means the wing root, the point where the wing attaches to the fuselage, must carry higher bending loads. A long wing may require more structural material, adding weight. It may flex more in turbulence, and may be more susceptible to aeroelastic problems such as flutter. Long wings also create practical issues. They require wider airport gates and taxiways. They may be difficult to transport, store, or operate from ships. For some aircraft, folding wingtips solve part of the storage problem, but they add hinges, weight, maintenance, and complexity. A shorter wing is usually stiffer and stronger for a given structural design. It can tolerate aggressive maneuvering and fit in smaller spaces. Its induced drag penalty may be acceptable if the aircraft spends much of its time at high speed, where parasite drag is more important than induced drag. This is why a long-winged glider and a compact fighter can both be highly optimized aircraft. They are optimized for different questions. Planform. The wing's shape from above. The planform is the wing's outline when viewed from above. Common planform shapes include rectangular, tapered, elliptical, swept, delta, variable sweep, forward swept, trapezoidal, blended wing body forms. The planform changes how lift is distributed across the wing, how the wing stalls, how efficiently it produces lift, how easy it is to manufacture, and how it performs at high speed. Rectangular wings. A rectangular wing has roughly the same chord from root to tip. Its advantages include simplicity, low manufacturing cost, and predictable geometry. It can also be designed to stall relatively gently near the root if the airfoil, twist, and other details are selected well. Its disadvantages can include less efficient lift distribution and greater structural material near the root than a tapered wing might require. It may also create a large portion of the lift toward the outer wing, where it contributes more to bending moment and where loss of lift can affect roll control. Still, the rectangular wing is not bad. It is often a sensible solution for a low-cost, low-speed airplane where simplicity and forgiving handling matter more than extracting every possible fraction of cruise efficiency. Tapered wings. A tapered wing becomes narrower toward the tip. The ratio of tip chord to root chord is called the taper ratio. A taper ratio of 1 means a rectangular wing. Tip chord equals root chord. A smaller taper ratio means the tip is narrower than the root. A taper ratio approaching 0 would mean the wing narrows almost to a point. Tapering can reduce structural weight because there is less wing area and less structure near the tip, where aerodynamic loads create large bending moments at the root. It can also improve lift distribution and reduce induced drag relative to a rectangular wing. But taper can create a stall challenge. A strongly tapered wing may carry a relatively high aerodynamic load near the tip. If the tip reaches its critical angle of attack before the root, the outer wing can stall first. Because the ailerons are typically near the tips, tip stall can reduce roll control and create an abrupt rolling tendency. Designers manage this with washout, meaning the tip is built at a lower incidence angle than the root. Different airfoil sections at the root and tip. Leading edge shape changes. Stall strips that intentionally trigger root separation first. Careful flap and aileron placement. Planform choices that avoid excessive tip loading. The lesson is that taper can offer efficiency and weight benefits, but it must be integrated with stall behavior. Elliptical wings. An elliptical wing has a smoothly curved outline, often widest near the root, and narrowing continuously toward rounded tips. The aerodynamic appeal of the elliptical planform is that it can create a lift distribution close to the ideal elliptical distribution, which minimizes induced drag for a given span and lift condition. But an elliptical outline can be difficult and expensive to manufacture. The curved spars, ribs, skins, and internal structure are more complicated than those of a straight tapered wing. It can also have stall behavior challenges if not carefully designed. The key engineering lesson is not that elliptical wings are always best. It is that engineers seek efficient lift distribution. A tapered wing with the right twist, airfoil, and wingtip treatment can approach the same aerodynamic goal while being easier to build and integrate. Delta wings. A delta wing is broadly triangular. It has a large root chord and a heavily swept leading edge, often with little or no separate horizontal tail. Delta wings are useful at high speed because sweep reduces the airflow component perpendicular to the leading edge, helping manage compressibility and shockwave effects. Their broad root also provides structural depth and internal volume for fuel, landing gear, and equipment. At low speed, delta wings often operate at high angle of attack. They can generate additional lift through strong vortices formed along their sharp leading edges. This is called vortex lift. It can make delta wing aircraft capable of high angle of attack flight, though their landing speeds may still be relatively high compared with a conventional low-speed wing. Delta wings are common in some supersonic aircraft because they combine high-speed performance, structural strength, and internal volume. They also come with trade-offs in low-speed handling, takeoff and landing characteristics, trim drag, and control design. Sweep, a high-speed strategy with low-speed costs. Sweep describes how far the wing angles backward or occasionally forward relative to the aircraft's side-to-side axis. A straight wing points nearly perpendicular to the fuselage. A swept wing angles rearward. The amount is often measured along a reference line such as the quarter chord line, meaning a line located 1/4 of the way back from the leading edge. Sweep is most strongly associated with high-speed flight, especially transonic flight near the speed of sound. At transonic speeds, parts of the airflow over a wing can become locally supersonic even when the aircraft as a whole is still flying below Mach 1. Shock waves may form, causing a sharp rise in drag and sometimes flow separation. This is one reason early high-speed aircraft encounter the so-called sound barrier. A swept wing helps because the airflow component perpendicular to the wing's leading edge is lower than the aircraft's full forward speed. In simple terms, the wing feels a lower effective speed in the direction most important to shock formation. This delays some compressibility effects and helps the aircraft fly faster before wave drag becomes severe. That is why most modern jet airliners have swept wings. Their cruise speeds are often near the transonic regime, where sweep is valuable, but sweep creates costs at low speed. A swept wing tends to have lower lift curve slope, meaning lift changes less strongly with angle of attack, greater tendency for spanwise flow, meaning air tends to move outward toward the tips, more challenging stall behavior, including possible tip stall, higher structural weight in some designs, more complex flap and slat systems, potentially less effective ailerons near stall, lower maximum lift without sophisticated high-lift devices. To compensate, airliners use leading-edge slats, multi-segment trailing-edge flaps, spoilers, twist, and careful aerodynamic tailoring. The wing must work efficiently at cruise, but still produce enough lift for takeoff and landing at manageable speeds. A straight-wing aircraft, by contrast, is often easier to design for low-speed lift and gentle stall characteristics. That is why many small propeller aircraft have straight or only mildly swept wings. Forward sweep, useful but structurally difficult. Most swept wings angle backward. A forward swept wing angles forward toward the nose. Forward sweep can offer attractive aerodynamic qualities, including potentially favorable stall behavior and improved airflow toward the wing root. It can also keep ailerons effective at high angle of attack, because the spanwise flow tends to move inward rather than outward. But forward sweep creates a severe structural problem called aeroelastic divergence. Aerodynamic forces can twist the wing in a way that increases its angle of attack, which creates more force, which twists it more. If not controlled, that feedback can become destructive. Modern composite materials can help, because engineers can tailor stiffness directionally. Even so, forward swept wings remain uncommon, because the structural and manufacturing challenges are substantial. They are a good reminder that aerodynamic desirability is only one part of wing design. A shape that looks promising in airflow may become impractical once structural flexibility enters the picture. Dihedral and anhedral, wings that tilt up or down. Look at an aircraft from the front. If the wingtips angle upward relative to the wing root, the wing has dihedral. If the tips angle downward, it has anhedral. Dihedral is primarily a tool for lateral stability, the aircraft's tendency to return toward wings level flight after a disturbance. Imagine an aircraft with dihedral flying level. A gust rolls it to the right. The aircraft is now slightly side-slipping. It is moving partly sideways through the air. The lower wing meets the airflow at a more favorable effective angle than the raised wing. It tends to produce more lift, creating a restoring roll moment toward level flight. This is called the dihedral effect. NASA defines dihedral as the upward angle of the wing panels from the root, and anhedral as the downward angle. Dihedral is a major contributor to lateral stability, though sweep and fuselage effects also play important roles. 2-1. A high-wing aircraft often gets some natural lateral stability from its fuselage and center of gravity arrangement, sometimes described as a pendulum or keel effect. Because the fuselage mass hangs below the wing, a high-wing design can be inherently more stable in roll. It may need less geometric dihedral than a low-wing design. A low-wing aircraft often needs more dihedral to achieve the same desired stability. Its wing position and fuselage interactions may provide less natural restoring tendency. Anhedral is used when an aircraft already has too much dihedral effect. This is common on some military transports, high-wing aircraft, and certain fighters. A high wing, significant sweep, or large vertical surfaces can create strong roll stability. Too much stability can make an aircraft resistant to rolling when the pilot wants to maneuver. Anhedral reduces the restoring tendency and improves handling balance. The ideal amount of dihedral is mission-dependent. A basic trainer may value strong self-righting tendencies. An aerobatic aircraft may use little or no dihedral because the pilot wants rapid, neutral roll response. A fighter may use anhedral to prevent excessive roll stability created by other geometric features. Incidence. How the wing is mounted. Wing incidence is the fixed angle between the wing's chord line and a reference line in the fuselage. It is a built-in mounting angle, unlike angle of attack, which changes during flight as the aircraft moves relative to the air. Incidence is usually fixed by the aircraft's structure. Why does this matter? An airplane's fuselage has an orientation that affects passenger comfort, pilot visibility, engine installation, radar alignment, cargo floor angle, and aerodynamic drag. Engineers can mount the wing at a particular incidence so that the aircraft's fuselage is approximately level during normal cruise while the wing operates at its preferred angle of attack. For example, a wing might be mounted with a few degrees of positive incidence. During cruise, the fuselage can appear nearly level relative to the horizon, while the wing still has the small positive angle of attack needed to generate lift. Incidence can also be selected to support takeoff and landing geometry. An aircraft must rotate on the runway without striking its tail, engines, or other components. The wing must reach a useful angle of attack during the takeoff roll without requiring an impractically large nose-up attitude. Incidence is therefore a quiet but important part of overall configuration design. Twist. Designing different parts of the wing to work differently. A wing does not have to operate at the same angle from root to tip. Twist deliberately changes the local angle of the wing along its span. The most common form is washout. With washout, the wingtip is set at a lower angle of incidence than the root. In effect, the root operates at a higher angle of attack than the tip during normal flight. The main reason is stall behavior. At high angle of attack, designers generally want the wing root to stall before the tip. If the root stalls first, the aircraft tends to give the pilot warning through buffet. The ailerons near the tips can remain effective longer. The aircraft is less likely to roll abruptly. The stall is more likely to produce a manageable nose-down tendency. If the tips stall first, the ailerons may lose effectiveness and one wing can drop sharply. This can lead to a spin if the aircraft is yawing. Washout helps the tips remain below their critical angle of attack when the root is approaching stall. It is one of the tools designers use to make an aircraft safer and more predictable at low speed. Washout can be geometric, meaning the physical wing structure is twisted. It can also be aerodynamic, meaning the wing uses different airfoils along the span. A tip airfoil may be chosen to stall later or behave more gently than a root airfoil. The same general idea can be used for cruise efficiency. A wing's local shape and angle can be tailored so each section carries an appropriate share of the load, minimizing drag and structural stress. However, twist is not free. It can reduce efficiency in some flight conditions, because not every part of the wing is always operating at its individual optimum. Once again, the designer is choosing a whole aircraft compromise. Wing placement, high wing, low wing, and mid-wing, where the wing attaches to the fuselage changes far more than appearance. The main categories are high wing configuration, low wing configuration, mid-wing configuration, shoulder wing configuration. Between high and mid placement, high wing aircraft. A high wing aircraft has wings attached near the top of the fuselage. This arrangement is common on utility aircraft, many trainers, cargo aircraft, and some military transports. Advantages can include good downward visibility for pilots and observers, easier access to the cabin or cargo door from the ground, more clearance between engines or propellers and rough terrain, potentially simpler landing gear placement in the fuselage, natural lateral stability from the high wing and fuselage arrangement, good suitability for unprepared airstrips. High wings can also make it easier to keep wing-mounted engines and propellers clear of debris. This is useful for aircraft that operate from gravel, grass, snow, or rough fields. But high wing designs can complicate access to the top of the wing for maintenance or refueling. They may also create structural challenges, because the wing carry-through structure must pass over or through the upper fuselage. Low-wing aircraft. A low-wing aircraft has the wing attached near the bottom of the fuselage. This arrangement is common on many business jets, airliners, fighters, and general aviation aircraft. Advantages can include easier access to engines mounted beneath the wing, convenient wing structure for mounting landing gear, good upward visibility from the cockpit, easier fuel storage in the wing with gravity-assisted fuel feed in some designs, structural arrangements that can work well with pressurized fuselages, a clean upper fuselage surface for cargo, passengers, or certain systems. Low-wing aircraft may require more dihedral to achieve the desired lateral stability. Their engines and wing tips can sit closer to the ground, creating clearance constraints. For an aircraft operating from rough fields, that may be a major disadvantage. Mid-wing aircraft. A mid-wing aircraft attaches the wing around the middle of the fuselage. Aerodynamically, a mid-wing can provide a clean intersection and favorable symmetry. It is sometimes used in fighters, aerobatic aircraft, and specialized designs, but it can be difficult to integrate with passengers, cargo, or large internal equipment, because the main wing structure passes directly through the fuselage, where useful interior space might otherwise be. This is less of a concern in a fighter or aerobatic airplane than in a passenger transport. The choice of wing placement affects aerodynamics, structures, landing gear, propulsion integration, cabin layout, maintenance, and mission use. It is a true systems-level decision. Wing fuselage, wing engine, and wing tail interaction. Aircraft parts do not operate independently. The wing changes the airflow around the fuselage, engines, and tail. The fuselage changes the flow around the wing. Engine exhaust and propeller slipstream can alter the flow over the wing and tail. Wing-fuselage interaction. At the wing root, the fuselage disrupts the airflow. Without careful shaping, this can create interference drag or localized separation. Designers use fairings and smooth blending to manage this. The wing root may look like a gradual curve rather than a hard intersection, because the smooth shape helps the airflow transition between the wing and body. The fuselage can also generate lift, especially at high angle of attack. In some aircraft, such as blended wing-body concepts, the distinction between wing and fuselage becomes less clear. The entire body contributes meaningfully to lift. Wing-engine interaction. An engine mounted under a wing affects the wing's airflow and structure. The pylon adds drag. The engine nacelle can create local pressure effects. The engine's weight creates bending loads on the wing. Exhaust flow can affect nearby surfaces, but underwing engines also offer advantages. They are easy to inspect and remove. Their mass can reduce certain wing bending loads by acting downward while lift acts upward. They can be mounted with sufficient ground clearance on an aircraft with tall landing gear. An engine mounted at the rear fuselage avoids some wing interference, but changes center of gravity management, tail airflow, noise, and maintenance access. Engine placement is an example of how geometry connects aerodynamics with structures, propulsion, and operations. Wing-tail interaction. The main wing creates downwash. The horizontal tail sits in air that has already been deflected by the wing, so its effective angle of attack differs from the free stream airflow. This matters because the tail is responsible for pitch stability and trim. A change in wing lift or flap setting changes downwash, which changes tail loading. That is why deploying flaps often produces a pitch change that must be corrected by trim or elevator input. The vertical tail is also affected by the fuselage, wing wake, engine placement, and sideslip. Designers must ensure it remains effective in challenging conditions, including one engine in operative flight for multi-engine aircraft. Geometry is always a compromise. It is tempting to ask which wing shape is best. The aerospace answer is always best for what? A high aspect ratio straight wing may be excellent for a glider, but inappropriate for a supersonic fighter. A swept wing may enable efficient transonic cruise, but require complex flaps and slats for low-speed operation. A tapered wing may reduce structural weight and induce drag but need washout to avoid tip stall. A high wing may help a utility aircraft operate from rough strips but complicate upper fuselage structure. A low wing may support convenient engine and landing gear installation, but offer less ground clearance. Dihedral may create comfortable roll stability, while anhedral may make a highly stable aircraft more responsive. No aircraft is designed by choosing one ideal wing variable at a time. Engineers evaluate combinations. Changing wingspan changes structural weight and airport compatibility. Changing sweep affects both cruise speed and stall behavior. Changing engine placement affects wing bending, noise, maintenance, and control in an engine failure. The goal is not to maximize a single aerodynamic parameter. The goal is to make the entire aircraft satisfy its mission safely and economically. A design thought experiment. Imagine you are designing 3 aircraft that all need to carry the same small payload. The first must loiter quietly for 10 hours over farmland while carrying a camera. You would likely choose a high aspect ratio fixed wing, low cruise speed, a slender fuselage, and perhaps an electric or hybrid power system. Efficiency and endurance matter most. The second must carry medical supplies from a city airport to short rural runways. You might choose a wing with substantial area, moderate aspect ratio, flaps, rugged landing gear, good propeller clearance, and perhaps a high wing layout. Low speed performance, rough field capability, and payload access matter most. The third must fly very fast at high altitude. You would likely choose Sweet, a thinner wing, relatively high wing loading, powerful propulsion, and sophisticated systems to manage high-speed drag. Efficient low-speed operation will still matter, but it will require more complex high-lift devices and careful control design. The physics of lift and drag do not change. The geometry does because the mission changes. Key takeaways. Wing geometry strongly influences lift, drag, stall behavior, stability, structural weight, and high-speed performance. Wing area helps determine how much lift the aircraft can produce at low speed. Wing loading is aircraft weight divided by wing area. It strongly affects stall speed and takeoff and landing performance. Wingspan and chord define the wing's overall proportions. Aspect ratio measures wing slenderness. Higher aspect ratio generally reduces induced drag, but creates structural and operational challenges. Planform is the wing's shape viewed from above. Rectangular, tapered, elliptical, swept, and delta wings each serve different purposes. Taper can improve structural and aerodynamic efficiency but may increase tip stall risk without careful design. Sweep is valuable near the speed of sound because it delays some compressibility effects, but it makes low-speed design more difficult. Dihedral improves lateral stability, and hedral reduces excessive stability when more maneuverability is desired. Incidence is the wing's fixed mounting angle relative to the fuselage. Twist, especially washout, helps the wing root stall before the tips and preserves roll control near stall. High wing, low wing, and mid-wing designs differ in visibility, stability, ground clearance, structural layout, propulsion integration, and mission suitability. The wing interacts with the fuselage, engines, and tail, so its geometry must be chosen as part of the whole aircraft. The next lesson, 1.6 Aircraft Aerodynamic Surfaces and Controls, explains how tails, elevators, ailerons, rudders, flaps, trim systems, spoilers, and other movable surfaces give an aircraft stability, control, and the ability to maneuver safely.
And that brings us to the end of this episode of the Drone Builders Collective. Thank you so much for hanging out and building with us today. If you enjoyed this episode, please take a quick second to like, subscribe, and leave us a review on your favorite podcast app. Your reviews help other builders find our hangar and join the crew. Don't let the conversation stop here. Leave a comment on your favorite app or send us an email with suggestions for future episodes. Keep your batteries charged, your props balanced, and your mind curious. Until next time, clear skies and happy building.